afternoon everyone. So, in today's lecture I am going to continue my discussion on fractional PDEs, and in today's lecture we are going to give you lots of examples arising of fractional PDEs arising in fluids, in mechanics, in quantum mechanics, in signal processing, in waves, in diffusion, in porous media, and today's lecture will be one of the last lectures on the discussion on fractional calculus. Okay, so moving on, let me right away start with an example. So, the example that I have in mind is the fractional diffusion equation on the half plane. So, this question is we have to solve fractional order diffusion equation in a semi-infinite domain, semi-infinite plane, let us say on the positive side. Okay. So, this is an IVP problem, an initial value problem given by the following PDE del u del t alpha. The fractional derivative of is equal to kappa times the second derivatives of u with respect to x, and of course, my alpha is between 0 and 1 and my x is positive and my t is non-negative. Then my initial conditions are as follows. I have that u of x at t equal to 0 is given to be 0 for all x positive in the entire domain, and the second I need two sets of boundary conditions for this second order PDE in space, and those are the solution at 0 comma t is given by u naught f of t. So, I specify a particular function on the plate, and this is for all values of time, and the second solution is, the second boundary condition is that the solution needs to be bounded for infinitely large value of the domain. Okay. So, we need to find a bounded solution to this problem. Okay. So, let me call this equation as 1 and let me call these boundary and initial conditions as 2. So, then let me straight away apply Laplace transform to 1, apply Laplace transform to 1 and 2, I get the following fractional order ODE. The ODE looks as follows. I have, so this is with respect to the variable t. I am applying Laplace transform with respect to the variable t, and I see that I get the following expression. This is s to the power alpha of u bar of s minus s to the power alpha minus 1 of u so u x comma 0. So, that is the solution at t equal to 0, and since alpha is from 0 to 1, we stop the Laplace transform up to 2 terms. Then this is also equal to well this will be also equal to kappa times u bar of s x x. Okay. So, then next before simplifying this further, I see that the solution at t equal to 0, the initial condition is 0. Okay. So, then this is applying the Laplace transform to, well, let me just do it step by step. So, first to my equation 1, I see that my Laplace transform reduces to the following ODE. So, I get d u bar, the second derivative with respect to space, is equal to s to the power alpha by kappa of u bar s. Okay, so then this is for all x positive. Okay, similarly, I apply my Laplace transform to 2 again with respect to the variable t. I get the following equation. I get that u tilde of 0 comma s is u naught f, let me call this as capital F of s with a bar, and then the solution goes to 0 as, so the solution must be bounded, and so is the Laplace transform. So, if I were to use, let me call this ODE, let me call this as 1 prime and let me call this as 2 prime. So, solving 1 prime and 2 prime, I get with subject to the condition that the solution must be bounded, I get the following solution to the ODE. So, solving 1 prime and 2 prime, I get the following solution to the ODE. I get that u bar of x comma s is u naught f bar of s times e to the power negative a x. Now, where my constant a is square root of s to the power alpha by kappa. Notice that this solution, notice that u bar goes to 0 as x goes to infinity. So, the solution is bounded. So, only the negative exponents are retained, so that this condition is satisfied. Okay, so, then the next step is to, let me call this as 3. So, the next step is to apply inverse transform, to 3 to come to the new solution as, so to come to the solution in the physical plane as u of x comma t is u naught, well then the integral of, this is the Laplace, well the Laplace inverse transpose of f bar of s times e to the power negative a x. Okay, so that will be nothing but the inverse transform of the product of two Laplace transform will give me a convolution. Convolution will be as follows. So, this is f of t minus tau g tau d tau. Now, I know that, well g is a, so g of t is the inverse transform, Laplace inverse transform of e to the power negative a x, and that is also where the a contains my variable s. So, where a is my square root of s to the power alpha by kappa. Okay, so, then well the solution is, well the solution is here. I have already found the solution to the fractional diffusion equation, which is given by 4. Now, the further evaluation of this integral given by 4 depends on the functional form of f as well as what is the order alpha. Now, in particular I can always discuss a particular case. In particular, if I am given that alpha is 1. So, in particular if I take alpha equal to 1, and let me further for simplification choose f is equal to 1. So, the functional form of both alpha and f, suppose they are given, and in that case I am left with the fact that the Laplace transform of the solution is u naught of e to the power negative of x times square root s by kappa divided by, so divided by s. Okay. So, f is 1. So, the f of s will be 1 by s. So, I see that u of x comma t is u naught times the, well for in this case I can always find the inverse transform. The inverse transform has been found in one of my previous lectures on Laplace transform. the inverse transform, let me write down the answer for this case. I get the solution as an error function, the error function complement of the following argument. So, the argument is x by square root, well 2 times square root of kappa t, kappa times t. Okay. So, I see that I see the following. So, if g, well, so this is the solution here, and further in this case I can write down my Green's function. So, notice that g is the Green's function in this semi infinite diffusion case. Okay. So, I can always write my Green's function. So, my Green's function is the Laplace inverse of e to the power negative x times square root s over kappa. So, that is the Laplace transform inverse, and that gives me, well, directly evaluating this inverse using my contour integral, I get the answer as follows. This is x by 2 square root pi by kappa t cube times e to the power negative x square by 4 kappa t. Okay. So, that completes the discussion here on fractional diffusion equation. Let me just move on to another example, that is on fractional Stokes, fractional Rayleigh and fractional equations in fluid flows. So, in the next example I am going to talk about fractional unsteady fractional Stokes and Rayleigh problem. So, fractional Stokes and Rayleigh problems in fluids. Okay. So, let us look at some examples. So, before I move ahead to look at the fractional case, let me just highlight what is the classical case of Stokes and Rayleigh problems. So, the classical Stokes problem or the regular PDE which governs the phenomena, the Stokes phenomena, is related to the unsteady boundary layers, the unsteady boundary layers, the unsteady boundary layer flows of viscous fluids, in a semi infinite domain, bounded by a plane. Let me say the plane is at z equal to 0 and oscillating with frequency omega. So, what I am given is that there is an infinite plate. Let us say this plate is located at z equal to 0, and typically in a Stokes problem this is oscillating with some frequency omega. Okay. So, we have some oscillation of the plate at this z equal to 0, and there is some fluid which is on top of this plate, and the fluid, we want to study the behavior of this fluid using the standard Navier-Stokes equation at a very low Reynolds number or close to 0, so 0 Reynolds number. Okay. So, let us start looking at this problem. So, let me just say, well, before I move ahead, so this is a Stokes problem here. So, this is the classical Stokes problem. The classical Rayleigh problem, is when omega is 0, that is when the plate is not moving at all. I want to study what is the behavior of the fluid above the plate. Okay. So, let us now consider the fractional Stokes / Rayleigh problem. So, the equation that I am considering, so let us describe the behavior of the flow. We have an unsteady fractional fractional boundary layer equation. Let me call the boundary layer as shorthand notation BL. So, I have a fractional boundary layer equation for fluids with velocity given by u of z comma t. Okay. So, in that case my fractional equation is as follows. So, del u del t alpha is equal to nu times del square u del z square. Okay. And of course, this is a semi infinite domain. So, z is positive and t is non negative, and I am further given the boundary conditions as follows. I am given that u of 0 comma t. So, the solution, the velocity on the plate is given by u times f of t. So, the fluid has a no slip boundary condition, which means that the velocity of the fluid is equal to the velocity of the plate, and the second condition is u of z comma t is bounded, which means that the solution decays to 0 as we take the coordinate to infinity, the physical plane, the physical domain to infinity. This is for all t. And then further we have, let me call this as 1, and let me call these boundary conditions as 2, and further we have the initial condition that the solution, let me call that initial condition by 3. The initial condition is that the solution at t equal to 0 is 0 for all values of the domain. So, if I were to apply, look at the solution, the first step would be right away to apply my Laplace transform of to 1 with respect to my variable t. Okay. When I do that, I get the following ODE. I get the ODE as s to the power alpha u bar of, so the physical variable z is retained, and I apply the Laplace transform on the time variable u bar of z comma s. This is nu times the second derivative of u bar with respect to z square. I see that z is from 0 to infinity, and then the second is that u bar at 0 comma s is, this is my initial, this is my boundary condition, u bar at 0 comma s is u times capital F of s. Okay. So, let me write this in another line. So, I get that u bar of 0 comma s is u times capital F of s. Okay. So, then further the second boundary condition says that u bar at z comma s should be bounded or goes to 0, decays to 0 when z goes to infinity. Okay. So, such is the solution that I am trying to find out. Okay. So, then if I were to, so this is my 1 prime and these are my boundary conditions 2 prime, and of course, my initial condition is my 3 prime is u bar, u bar at s equal to 0 is 0. Okay. So, then I see that if I solve all these equations 1 prime, 2 prime and 3 prime, these are all ODEs with given conditions. I see that my solution u bar of k comma, so let me just even before I solve this, I see that this is an ODE, but I have the Laplace transform with respect to time and I have retained my physical variable. So, even before solving, let me just say that let me transform even my physical spatial variable. So, since we know that the solution is a given condition, there is a Dirichlet condition on the plate, I am going to use my sign transform to transform this physical space z into the Fourier space. Okay, so apply Fourier sine transform as follows to come to the complete transform domain. So, what I have is the following. I see that after applying the sine transform, so let me denote it by u bar s. So, s denotes the sine transformed solution of the transform variable k comma s, where k is the transform variable with respect to space and s is the transform variable with respect to time. I get that this is also equal to, after applying all my initial and boundary conditions, I get that this is square root 2 by pi times nu times u times the following fraction. It is k times f, let me just say that this is f bar of s divided by s to the power alpha plus nu times k square. Okay. So, notice that this k is arising due to the fact that the solution is 0 at time point t equal to 0. Okay. So, which means that this particular form of this transformed solution takes care into account all my boundary conditions and initial conditions. Okay. So, we see that as k goes to infinity, I also have the solution decaying to 0. Okay, or sorry. So, this particular factor here, k equal to 0, denotes the solution at z equal to infinity. So, I see that, note that this k equal to 0 here is equivalent to saying that the solution u bar at z comma s goes to 0 as z goes to infinity. So, that is equivalent to our Tauberian theorem, okay, for the Fourier case. Okay, so then the next step is to apply the Fourier inverse transform. Okay. So, this was using our Tauberian theorem. Okay, so then let me write away. So, before I move ahead, I just want to highlight that this is the sine transform. So, let me just recap what is my sine transform. So, recall that my sine transform, Fourier sine transform f of s of u of x is given by square root 2 by pi integral 0 to infinity sine k x f of x dx. Okay. And this is particularly useful when we have a Dirichlet boundary condition, which is the case in our situation, a Dirichlet boundary condition. Okay, so let me call this expression as 4, and I want to invert this expression 4 with respect to the Fourier and the Laplace transform. So, when we do that, I get the following. Let me just apply the inverse Laplace and Fourier transform. So, what I have is the following. I have, so apply Laplace, so inverse Laplace and inverse Fourier transform right away. So, inverse Laplace and Fourier transform, and I get the following solution. I see that this is the solution is u of z comma t is this factor, which is a constant 2 by pi times nu, the kinematic viscosity, times u times the Fourier integral, the sine integral 0 to infinity k times sine k z dz times the Laplace integral, well, the Laplace integral, the Laplace transform will give me right away a convolution. So, the Laplace convolution integral is as follows: f of t minus tau, and then due to the factor that we had, I am going to get a Maytag-Leffler expansion. So, I have the following: t tau to the power alpha minus 1 times e to the power e of alpha comma alpha of nu k square tau to the power alpha, okay, d tau. Okay, so then we can proceed a little bit further by assuming certain functional forms of f. Okay. So, let me just look at some specific cases.